Hello and welcome to another Arlington High School Math 4 Honors lesson. I'm Kirk Weiler, and today we're going to be looking at Unit 6, Lesson Number 4, on the full sinusoidal modeling. As I pointed out in the last lesson, sinusoidal models, or models that primarily rely on the sine and the cosine functions, are really fascinating, and they describe an amazing number of phenomena that are in the real world, including sound, light, and other things that come in waves. So we're going to be exploring a little bit more today about these models. Again, the worksheet in PDF form, plus a homework, can be found by clicking on the video's description. And as always, this is at the pre-calculus level, so the assumption is that you've seen a little bit of this material before. Anyway, let's take a look at where we're going with this. So in a full sinusoidal model, what we've got going on is we've got four parameters: an A, a B, an H, and a K. All right, and we want to make sure that we know what each one of those things does. We've already seen A and K. Let's review. The absolute value of A is the amplitude. It's how much that the trig curve stretches or rises and falls below the midline. So if I've got some random trig curve, don't worry about sine or cosine, and here's my midline, then my amplitude, or the absolute value of A, is this. By the way, the reason that we always specify the absolute value of A is because the amplitude is a distance, it's a positive. All right, A itself can be negative, which would reflect the graph across the midline, but that's it. Now the other one that we know is K, and of course now what I've done is I've written over where K was supposed to appear. So let me get rid of that. All right, K, as we know, is the midline. So in other words, if I've got some type of a sinusoidal curve whose midline is not the x-axis, then this would be the value of K. K can be both positive and negative. So of course, the real issue then becomes, what are H and K? All right, so let's take a look at exercise number 1. In number 1, it says, in the last lesson we looked at A and K, and here we're going to talk about B and H, which we learned about in a previous course. The first question is, what's the B, right? So in this model, what does B do, what's it called, and how does it relate to the period of the function? The period, remember, is the amount of horizontal distance. I often think about the horizontal axis in these models as being time. So it's the amount of horizontal distance that it takes before the curve repeats itself, and it has a relationship to B. The second question then is, what's H and what's its technical name? Pause the video now if you need to in order to think about both of these. I'm going to get rid of the blue here, and then we're going to talk about them. All right, so pause the video. All right, let's take a look. B, turn my pen on. B is known as the frequency of the graph. All right, and frequency is a good word because it literally controls how frequently or how many times a sinusoidal model will complete a full cycle in 2 pi radians. So it's how many complete cycles in 2 pi radians. Many times students don't memorize that. What they memorize is that the frequency and the period have a very important relationship. They have an inverse relationship. The product of the frequency with the period is always 2 pi radians. Of course, we can solve this very quickly for either one of these. The frequency thus is always 2 pi divided by the period, and the period likewise is always 2 pi divided by the frequency. All right, this is really kind of important because oftentimes in an equation you can see the frequency, but you don't know the period. And on a graph, you oftentimes can read off the period, but you don't know the frequency, the B. And obviously what students do a lot of times is get the two confused. By the way, what that constant does that's multiplying x, and it really is multiplying x, I know you have the subtracting h in there, but think about distributing the b through, is that it horizontally dilates the function. I think of it as like an accordion, like this. Anyway, let's take a look at letter B. what's the meaning of h, right? Now, from just a general function perspective, of course, what h is it's the horizontal shift. All right. Last year, you may have called it the phase shift. That was something, phone's ringing, we're going to have to edit this out, but we will. There'll be a little funny break in the video. I apologize for that. All right, I apologize for the irritating time shift there. That's what happens when I get interrupted by a telephone call. I have to splice the video, pull out the chunk where I just talked to Mrs. Wright on the phone, and then the two don't necessarily match up very well. Anyway, back to what h is. H is the horizontal shift of the function, sometimes called the phase shift. I don't like it being called the phase shift, I'll be honest with you. I've seen in different textbooks, especially physics ones, that horizontal shift is not referred to as the phase shift. But either way, it's simply how we shift our entire graph in the horizontal direction. Of the three, the amplitude, the frequency, and the midline, the horizontal shift is, in my opinion, the least important of them all. It shows up the least often in the models. It does have some importance, and we're going to work with some modeling later on in this unit where we'll need the horizontal shift, but we're just going to work with it a little bit today. All right. I'm going to be scrubbing out this screen in a moment, so copy down what you need. Do you have it? Okay, we're going to scrub. And it's gone. Let's go to the next page. Okay, so let's start to apply a little bit of this. Exercise 2 gives us the function y equals 4 times the cosine of 6t, and it asks us to sketch two full periods to the right of the y-axis. Assume your input has units of radians. By the way, that's important because the only reason that this actually works is because we're in radians. If we were in degrees, the only thing that would change is that b times p would have to be equal to 360. And I hope you can understand why. Anyway, let's take a look at what we really have. I'm going to write down a little bit bigger. 4 times the cosine of 6t. I've got all the space in the world here. So one thing that we noticed right away, right, let's tackle what's easy, is that the midline continues to be y equals 0. We've had no vertical shift, so this curve's going to go above and below that midline. Likewise, we have no horizontal shift, right? We haven't subtracted anything from the t before multiplying it by 6. All right, so all we really have to worry about is an amplitude equaling to 4 and a frequency equaling 6. So you can already kind of picture what's happening in the y direction, right? It's going 6 above the x-axis, 6 below, I'm sorry, my bad. It's going 4 above the x-axis, 4 below the x-axis, 4 above, 4 below, right? But the question is, how quickly is it finishing off a full cycle? That's the period, right? So what I know is I know that the period will always be 2 pi divided by 6, right? Always 2 pi divided by my frequency. Of course, that reduces nicely to pi over 3. So let's sketch this thing. All right, I know that it's going to be going above and below my x-axis, right? I know that I'm going to complete a full cycle in pi over 3. Trig graphs come in quarters. This would be then 2 pi over 3, right? Cosine. Cosine starts at its maximum, right? Unlike sine, which starts at its midline. So I know it's going to be at its maximum at this point. A quarter of the way through, it will be at its midline. Halfway through, it'll be at its minimum. 3/4 back to the midline, and then back to the max. There's probably almost no way I'm going to connect these smoothly, but you know, one of these days I might get it. Oh, I missed it. Boy, that's irritating. Anyway, I was supposed to go through this point and this point. I apologize for that. One of these days I'm going to learn how to draw a nice smooth graph on my tablet, but it's tough to do. So anyway, that's roughly what your graph is supposed to look like, with this section being a little bit more like that, let's say, and just erasing this. Okay. Why didn't the eraser keep going? I don't know. Anyway, and see, I erased too much. Anyway, take a look at the screen, pause it if you need to, because we're going to scrub out the text in a second. Are you ready? Okay. All right, let's go on to problem number 3. Okay, now problem number 2, and I like thinking big pictures here, right? Problem number 2, I was given an equation, and I needed to translate that into a graph. Problem number 3, we're going to go in reverse. We're going to take a graph, and we're going to translate it back into an equation. Okay, might as well write down the full model. Maybe we won't need everything, but maybe we will. So the full model, y equals a. We'll write down sine, but of course maybe it's cosine that we want to use. B times x minus h plus k. Now ultimately, when you figure out the equation of a sinusoidal model, it all boils down to figuring out these 4 things. Right? I got to figure out each one of these. Put a little question mark in front of each. You can figure them out in any order you want. I tend to go with the easiest first, okay? And to me, the easiest is always figuring out the value of a and the value of k, all right? The vertical don't depend on the horizontal, and the horizontal don't depend on the vertical. So remember, a is the amplitude. Well, the absolute value of a is the amplitude. K is the midline. Why don't you pause the video for a moment and see if you can figure out the values of a and k. All right, let's go through them. Many different ways to do it. I'm going to figure out the value of a by taking my maximum y value, which is 18, subtracting my minimum y value, which is 2, and dividing by 2. Remember, doing that subtraction tells me the vertical separation between the max and the min, and the a value, well, at least the absolute value of a would be half of that. All right, midline, that's going to be easy. Always the average of the peak and the lowest y values. That's 20 divided by 2. That gives me a vertical shift of 10. So those 2 are done. I'm not going to even worry about them. They're going to have no effect on the horizontal. But now let's think about the horizontal. Now, I always leave h for last. Always. I go for the frequency next. Now the frequency, again, depends on the period. In the last problem, we knew what the frequency was and we wanted the period. Here, we're going to figure out what the period is by looking at the graph, and we'll use that to calculate b. So what I would like you to do is pause the video right now and see if you can figure out what the value of the period is from the graph. All right, let's go ahead and go through it. I'm going to switch colors really quick over to red. One of these days, other colors are going to get some territory. Now what do we know? We know that's got an x value of 3. We know that's got an x value of 9. So we know their separation is 6 units. But that's not a period. That is only half of a period, right? Always take advantage of trig curves, yes? So the symmetry of trig curves tells me that my period is 12. 12 what? I don't really know. I'm going to go back to blue. But what I can now say is that my frequency must be 2 pi divided by 12 or pi divided by 6. I actually like to leave my frequency in 2 pi divided by p form because then I can see what my period is, right? I can see it. Those are supposed to be eyeballs looking upward. I don't know why I just did that. Okay, last but not least, or maybe last and least, I don't know, is the value of h. Now, h is tricky because a, b, and k for this problem are unique. Not entirely true. I could make a plus or minus 8, but I'm probably going to make it 8. H, though, depends on what kind of trig function you're going with, and to a certain extent, it also depends on what your value of a is. So, if I assume that I am using sine, I'm not going with cosine, and I assume that a is positive, I'd like you to think about what the value of h is. So pause the video. Alright, now remember, I'm assuming a is positive, and I'm assuming I'm using the sine value. That gives me an h of 0. Now, how do I know h is 0? How do I know I haven't shifted it at all? Well, remember, sine starts at its midline. Now, I've drawn this thing like it starts at the midline, but here's how I would know for certain that it starts at the midline, right? Take a look at that period. It's really important to always keep in your mind what 1/4 of the period is, what the period divided by 4 is, because trig graphs come in quarters. So every 3 units along the x-axis, we go from a min to the midline, from the midline to the max, from the max back down to the midline. So because I know that this x-coordinate is 3, I know I'm at the midline when I have an x-coordinate of 0. Because this starts from the midline, I know that I can consider h0. So let's write down that final model. Y equals 8 times the sine of 2 pi divided by 12 times x plus 10. And there it is, the full sinusoidal model. All right, without a significant h. Throw that into your graphing calculator, check that it goes through 318 and 9.2. Just make sure you're in radian mode, otherwise it's going to think you're talking to Reese. Okay, I'm going to scrub out the text, so take a look at it, pause the video if you need to. Okay, I'm scrubbing. Next page. All right, let's deal a little bit with h. Okay, exercise 4 says, how can we produce the graph of y equals the sine of 3t plus pi over 8 from the graph of y equals sine of 3t? Okay, so I want you to pause the video for a little bit and think about how you must have horizontally shifted y equals sine 3t to get y equals sine 3t plus pi over 8. All right, now, if you wrote down that you shift negative pi over 8 or pi over 8 to the left, I got some bad news. You're not correct. Okay, so if you said pi over 8 units to the left, what I'd like you to do is pause the video again and remember that when I'm looking at a sinusoidal model, right, when I'm looking at one of these, to identify the horizontal shift, I have to know what I've either added or subtracted to the input variable before I've done anything else to it. Unfortunately, in this form, I've actually multiplied the input variable by 3 before I added the pi over 8, so it's not of this form. So pause the video and see what you can get. I'm going to do a little erasing. All right, let's take a look. So the way that you handle something like this is you have to make it match this form. So I'm going to actually factor 3 out. Now this is tricky, right? Because what goes here, right? What goes here? I got to think about it. It's actually pi divided by 24, right? Think about it. If I distributed this back through, right, I'd get 3t plus 3 times pi over 24, but that would leave me with pi over 8. So in fact, what we have is a horizontal shift, pi divided by 24 to the left. And again, it's to the left because we're adding. Remember how horizontal shifts kind of work the opposite of the way you'd expect. Okay, I'm going to scrub that text out. You ready? All right, let's move on to the next page. Okay, so now what we're going to do is we're going to do some just real modeling. We're going to take a physical scenario that is periodic in nature, meaning that it repeats itself, and we're going to try to model it with one of these sinusoidal curves. So let's take a look at exercise 5. A person boards a Ferris wheel whose diameter is 90 feet at its lowest point, which is 8 feet above the ground. The Ferris wheel makes a complete rotation every 6 minutes and travels counterclockwise. Graph 2-fold periods of a person's height on this Ferris wheel, and then write a possible formula for h. Okay, you know what I think I'm going to do? I think I'm going to draw the Ferris wheel first. Why can I draw a good circle there, but I can't when I'm doing the unit circle diagram? Jeez. All right, so a person gets on down here. What did we know? that was 8 feet above the ground. 8 feet above the ground? Sure. We also know that the diameter of this thing is 90 feet. And we're traveling counterclockwise. Right, something like this. One whole rotation takes 6 minutes. So let's graph this thing, shall we? Let's see what it looks like. Beautiful. All right, my height above the ground versus time. Well, we know it's going to finish in 6 minutes, so let's do, what do we need? 2 full periods? Yep, let's go 12. What do I know? I know I get on 8 feet above the ground. I know after 3 minutes I have to be at the top. What is the top? Well, that's going to be 90 plus 8, right? It's going to be 98. Then, after 6 minutes, I'll be back at the 8. After 9 minutes, I'll be back at the top. And after 12 minutes, I'll be back at the 8. I might want to be kind of thinking about these midpoints too, right? They kind of matter as well. But okay, big money, big money, big money, no whammies. Yes. Okay, go inflection point. You know, that's about as good as I've ever done. All right, so there's our graph, right? 2 full cycles. Got overconfident, right? 1 full cycle here, 1 full cycle here. Now what we want to do is we want to come up with a possible formula. All right, now remember we got to figure out a bunch of different things. We got to figure out A. We got to figure out B. We have to figure out H. We have to figure out K. And for me, I always do these first. It really doesn't matter which one. I always do this one third, and I'll always do this last, and we'll talk about why again. Okay? Let's figure them out. Why don't you pause the video right now, figure out what A and K and B are, but why don't you leave H unless you're absolutely confident? All right, let's go through A, B, and K. More appropriately, let's go through the absolute value of A. All right, remember the amplitude. Take your highest y value, subtract your lowest y value, divide by 2. 90 divided by 2, 45. By the way, if you didn't realize this, of course, 45 is the radius, and that makes then all the sense in the world. The radius of the circle you're traveling around is always your amplitude, right? The center of that Ferris wheel, that's your midline. But the radius then tells you how far above and below you go, right? All right, let's figure out the midline. I'm going to actually draw it on there. I love having the midline on, right? In fact, it's very, very easy now that I know my amplitude. My typical way of finding the midline is I do the average, right? I take the top plus the bottom y values, add them together. 106 divided by 2, 53. But another way, of course, figuring out that the midline is 53 is you could just add the amplitude onto the minimum or subtract it from the maximum. So, got it? Got it. All right, let's figure out B. In order to figure out B, that's going to be simple enough, right? We're going to use the relationship that says that B can always be found by taking 2 pi and dividing it by the period. The period in this case, exactly what it was in the last problem, sorry. Well, not the last problem, but the previous one, is 6, so our frequency is 2 pi over 6. And again, I would leave it like that. Now the H, and here's why H is tricky. Again, H could be almost anything you want it to be, depending on whether you're talking about modeling with the sine function, the negative sine function, the cosine function, or the negative cosine function. Wait, did I say the negative cosine? Anyway, whatever. You got 4 choices. It's even worse than that because of how often you can shift. So, what do we go with first? All right. Let's go with the normal sine function. It's actually the one that I would like people to model with the most. Now, how do I figure out H? Here's what I do. The normal sine function starts from the midline and rises out of it, all right? So if I want to use a normal sine function, what I have to do is I have to have a curve that is shifted 1.5 units to the right. So one correct equation would be to say that y is equal to 45 times the sine of 2 pi divided by 6 times t minus 1.5 plus 53. right? And that'll work fine because it means that what'll happen is that the sine will start at 1.5 and rise out of it. All right, easy enough. Why don't we go with a fundamental cosine? Now remember, cosine starts at its maximum. And the first maximum I have is right here, right? So if I want to just model with the positive cosine, what I need to do is I need to have a horizontal shift of 3 units. So this is a perfectly good equation. 45 times the cosine of 2 pi divided by 6 times t minus 3 plus 53. That works too. Oh, it doesn't end there. Let's do all 4 of them. Maybe not on the next problem, but on this one. Let's do one that has no horizontal shift at all. If I have no horizontal shift at all, it means I have to be starting from t equals 0. But the question is, what starts from t equals 0? Hopefully you'd realize it's the negative cosine function. For lack of a better term, it starts at its minimum. So here's where we let a go negative. Now, because I don't have to shift at all, right, I'll just get something like this with no shift included, no horizontal shift included, and I have that equation. The last one would be the negative sine. Negative sine starts at its midline and then decreases out of it. So what I would need to know in that case is what this is. That's at 4.5. So we would get y equals 45 times the sine. Oops, I'm sorry, this is the negative sine. So it's negative 45 times sine of 2 pi divided by 6 times t minus 4.5 plus 53. I kind of like the red and blue. It's the Christmas season right now as I record the video, and I like all the colors. They're pretty. Anyway, whatever. Take a look at that. All 4 of those equations are exactly the same, even though they look quite different. One thing that would be interesting to do if you have the time is pause the video, put all 4 of those into your graphing calculator, make sure you're in radian mode, get a good window, and then hit graph. And what you should see is 4 identical graphs, like just laying on top of each other. So actually what you'll see is 1 graph. All right, I'm going to scrub out the text. So pause the video now if you need to. Okay, here goes the scrub. All right, we've got one last problem to do. Tides are a periodic phenomenon. I love tides. They rise, they fall. It's all kind of this beautiful cyclical process that occurs due to the relationship of where the moon is to the earth. So they're a wonderful thing that can be modeled sinusoidally. So a little bit simplistic, but we're told that the tides are a phenomenon whose period is 12 hours. So from one high tide to the next high tide, exactly 12 hours. It's not actually the true, but please forgive me for simplifying it. At t equals 0, we're going to say that the tide is at its lowest point with a depth of 2 feet. After 6 hours, the tide is at its highest point. Makes sense since the period is 12 hours long at a depth of 14 feet. Again, we're going to sketch 2 full periods and then we're going to come up with an equation. Why don't you pause the video and do the whole thing? Sketch the 2 full periods, try to come up with an equation, try to come up with a couple of equations if you want to, and then we'll take a look, okay? Pause the video now. Okay, let's go through it. First, let's do the sketch. Sketches are really critical. Even if I wasn't asked for a sketch on this, red, I think we'll just stay in red. Even if I wasn't asked for a sketch on this, I would still do one to get a feeling for what's going on. All right, I want to know the depth of the water over time. I know that it cycles every 12 hours, so I'll get my 12 and 24 on there. I know at t equals 0, we're at our lowest depth, which is 2 feet. 6 hours later, we're at our highest depth, or greatest depth, which is 14 feet. Remember, this is the depth of the water. Back at 12, I must be back down. This should look familiar to what we just did. What's this here? Oh, 18. Right, okay. At 18, I'd be back at the top, and at 24, back to the bottom. Oh, why not? Let's mix a little bit. We'll now draw the curve in blue. Trying so hard, missed. And of course that one looks like it's above it. This is probably what the tides really look like. It's supposed to be symmetric. Anyway, I'm tired. So let's take a look at what we have, besides a really ugly sinusoidal graph. All right, we gotta do the full model. You know from the last problem, we gotta figure out A. we've got to figure out K. We've got to figure out B. We've got to figure out H. All right, I always do these two first, do this one third, do this one last. Okay, let's do it. So the absolute value of A, the peak value minus the minimum value divided by 2, that's 12 divided by 2, that gives us 6. The vertical shift, the average of the highest value and the slowest value, that's 16 divided by 2, that's 8. I'm going to just draw that on. I love having my midline on there. And then I can see that rise above and fall below, rise above, fall below. Okay, let's figure out our frequency. Our frequency is always 2 pi divided by the period. In this case, the period is 12 hours. I'm going to leave it as just 2 pi divided by 12. Make it into pi over 6 if you'd like. Whatever. Now for H. This is very, very similar to the last problem. So the question is, what do you want to use? Positive sine, positive cosine, negative cosine. I'm going to go with positive sine just so that we can actually get a little bit of a shift in here. You could go with negative sine and negative cosine and have no horizontal shift. I'm going to be going with positive sine. So I'm going to shift it 3 units to the right. So we're going to have y equals 6 times the sine of 2 pi divided by 12 times t minus 3, that was my horizontal shift, plus 8. Again, one of the nice things about taking a graph and translating it into an equation is that if you've got your graphing calculator, you can now put that into your graphing calculator in radian mode, graph it, and see if it looks like the one that you just sketched by hand. All right, but that's it. Again, there's 3 more equations that seem appropriate, but honestly, because it keeps repeating itself, there's actually an infinite amount of correct equations. So let's stop there. I'm going to scrub out the text in a second, copy down what you need to. Okay, here we go. All right. Well, I want to thank you for joining me for another Arlington High School Math 4 Honors lesson. This has been Unit number 6, Lesson number 4 on full sinusoidal modeling. Please feel free to click on the video's description in order to access a PDF file that's got the worksheet used in this lesson. Until next time, I'm Kirk Weiler. Keep thinking and keep solving problems.